Good morning. Welcome to Krishna's classroom. Let us return to our series of lectures. In this talk, I wish to introduce the concept of measure zero, which is very often invoked while working on integration. Let's start with a small example. Suppose f is continuous function on 0. I'm talking about real valued functions. Okay. So f is from now let me define G by Gx equal to whenever x belongs to intersection the irrationals and equal to 0 that means I am going to modify the function f to a new function g. It's like you have a continuous function. Now suppose this is a rational point q. At q you define this is f. Define at all points qi, because it's a countable set. You take the function to be 0. So the new function is going to be the f at all irrational points and is 0 at all these. So g and f differs. So gx is different from g is different from f. G differs f on rational points. Now let us consider the integral of g and f. See that integral of on the interval I am talking about Lebesgue function. Lebesgue measure. I can split this is finite because we are taking a continuous function. Now we will compute integral g. This is equal to integral Q GDM. Now this turns out to be, see, on Q complement intersection 0, 1, G is equal to F. This is equal to F plus integral Q, this is 0, or I just let me change this slightly. Let me keep this 1, okay, because otherwise, so this is equal to 1. Okay. Now what about this? Equal to integral Q complement plus, what is it? This is 1 into measure of and measure of this is 0, therefore this is equal to integral complement of F. Now you can see that, easily see that integral of F is also equal to integral of complement of F plus integral of F. But this is again equal to 0. Why? Because it does not matter what the value of the function f is at these points, this is equal to integral of what does this mean? So when f and g differ only on a set of 0 of measure 0, then you see the integrals do not change. Thus here the countable set of points, rational points have measure 0. So we have this particular insight into the problem. Now here you have two different functions. If they differ only on a set of measures 0, then their integrals are the same. Okay, so it's a property of the two functions f and g that they differ on a set of measure 0. Now we shall try to work out this. So as far as integral is concerned, to replace a function by another function which differs from the given function only on a set of measure 0, then the integral it won't affect it. Now this is the moral of the story. So let us now work on this. The systematic analysis of this aspect. Make a definition. Let P denote a given property. Which may be or may not be true at a point now let us examine some examples for this. First example is, suppose f is a real valued function. Okay. Then fx greater than or equal to 0 is a property and the set of points where this property holds, we write it as, so we have is a property may be or may not be another example is you have a sequence of functions f. On the interval 0, 1. I mean, not necessarily, I am just taking some interval 0. It's not necessarily that all the problems are set on interval 0, 1. Now, see, we look at this one. The convergence of this. F and x converges. Now, once again, this is a property. You can give so many examples. You have two functions f and g defined on the interval 0, 1, real valued functions. Then fx is different from gx, or fx is equal to gx for some x's. That is possible. Okay. Then to see that, once again, this is an example of a property which may be or may not be valid at every point. It will be maybe valid at some points. So that's about the properties. Now we go further. We talk about what is called a set of measures. So let x script m mu be a measure space. That means you have a non-empty set X, a sigma algebra on that, and a measure on that. Even if it is an empty set, still you can talk about a sigma algebra consisting of only the empty set, empty subset of that, and then the measure can be set as 0, because measure has the property that on a set of measures on the empty set the measure has to be 0. Okay. So this is what we have, but if you want to get something non-trivial, then you need X to be a non-empty set. M is a given sigma algebra and mu is a measure. So this is what you call a measure space. So this is the measure space on which we will be working. So now we define definition. A property P is said to hold almost everywhere on a set E means that there exists a subset N such that N is a subset of E and P holds at every point of E minus N. What does it mean? See, E is a given subset and we take E to be an element of M. Now what you have is, there is a subset N belonging to M and N is contained in it. and the measure of 0. Now suppose the property, whatever property you are talking about, is valid on E minus n and not valid on, okay, then we say that the property E is valid almost everywhere in, that means the only place where it possibly not valid is on a set of measures 0. That is, P is valid everywhere except possibly on a set of measures 0. Then we say that P holds almost everywhere. Now here I use the abbreviation A dot E. A almost A E everywhere. That's the meaning of that. Now, one of the things that is obvious is that, see, we are talking about a subset whose measure is 0. Okay. Therefore, so we make a remark, says that the property is valid almost everywhere on E. Suppose the property P is valid almost everywhere on E, then it depends on whether n has its measure 0 or not. So depends on the measure because we need this condition that I think I have missed the point. N is contained in E and measure of n equal to 0. That is important. Okay. So the measure of n has to be 0. So it really depends on mu. You use a different measure, the subset M may not be. For example, if zero, but suppose you take the counting measure on the same interval, okay, and then look at a finite set of points. What will be the measure of that? It is going to be 0 because it depends on the number of elements in that subset. So really depends on mu. Hence we shall write almost everywhere indicates that it is related to the measure that we choose. In the context, in some context, we are is implied or understood that you are talking about the property which is valid almost everywhere. Okay, now let me give some examples. Let with respect to the Lebesgue measure, and if mu of the set on which f differs from G is equal to 0, then we say that f is equal to almost everywhere with reference to the measure mu on. Now that is the meaning of that. Another example, okay, yeah, right. So we will now look at the properties of this, any structural property that we can see for this f equal to G almost everywhere. So this relation that is f is equal to G almost everywhere. Maybe denoted by F is in G. Now we claim is an equivalence. That is the first observation. F is equal to G almost everywhere with respect to mu is indeed an equivalence relation. That's obvious. See, it's easy to see that if F is equivalent because it's only on the empty set that they differ, which has measure 0. So the first property, obvious. The second property is F is equivalent to G, then that implies G is equivalent to. Suppose N is the set on which F and G differs, then it's the same set on which G and F differs. And suppose N has measure 0 with respect to mu, then you see that if F is equal to G almost everywhere with respect to mu, which implies G is equal to F almost everywhere. The third property that we want is transitivity. That is, suppose F is now this uses the fact that union of two sets of measure 0 is also one such F differs from G on a set A and G differs from H on a set B. On a set B. Then you see on A union B, you see that F differs from possibly from H, or at least it is going to be contained in that, which implies, and you know that the union of two sets of measure 0 has measure 0, therefore F differs from G on a set of measure 0. So this is the property that we make use of. Now we observe that F is equivalent to G, then for every E belonging to the sigma algebra M, we have integral of that means two functions which differ almost, which agree almost everywhere on E. That means they possibly differ only on a set of measure 0, will have the same integral. Okay, so we shall just very quick this. And this is the sort of example that we looked at the beginning, motivates the problem. let X or I will put say now assume now E is essentially equal to E minus N union E minus N union E intersection N. Suppose N is something like this, then you see that E minus N will be this portion and union E intersection N is this portion. So that will be F is equal to G and mu of zero. Therefore, we will use this integral over E equal to integral over E minus N P mu. And this you can see that what have we said on E minus N F is equal to G, therefore the integrand is 0 here on this, and on this you see F is not necessarily equal to G, but the measure of N is 0. Therefore you see that this integral is, this is what we did in the first example. Measure of N okay. Therefore, you see that measure of the Z intersection N is contained. E is measurable, N is measurable. Therefore, E intersection N is a measurable subset of N. The measure of intersection N is less than or equal to the measure of N, which is already 0, and therefore this is also 0. Therefore, what we get? This is what we wanted to assert. Okay. Now we make some demand. It may happen that a set N, measure of N equal to 0, have a subset E, that is E is contained in N, such, but E is not. E does not belong to E is not measurable. Now this is an inconvenience. This quite often you come across this. You can artificially construct some example, but even with the standard measures, sometimes you use these properties. Now to get over the problems that come out of this particular scenario, we shall define E contained in N, measure of E equal to 0, then measure of now this is a definition that you can. So in other words, we are now stretching out the measure onto all subsets mesh of sets with a 0 measure. So those such sets may not be measurable originally, but we are now going to. So we shall see how technically we do this. In other words, we are going to carry such E's also into the measurable class or to the sigma algebra, or we are going to enlarge the class of sigma algebra. Okay, so we have the sigma algebra, given sigma algebra script M, and we are going to put in new subsets into that and make it a larger class. But will you get a sigma algebra? This is the problem. Suppose you include all such sets also into it, do you get a sigma algebra? What happens is we do get. And this is the interesting part. So let us work on that. Okay. So the problem is we are given the sigma algebra and we may have sets of measure 0 having some subsets which are not measurable. Now we bring in these sets also into the collection of and construct a new sigma algebra and also postulate that the measure on these subsets 0 consistent with the property that if A and B are two measurable sets, A contained in B, the measure of A is contained in is less than or equal to the measure of. So that is the whole consistency problem that we take care of. Okay, so we postulate every subset of a set of measure 0 is also measurable and the measure of such set and set its measure as. So this is what we find. Now the whole lot of questions come out. We have now got already a sigma algebra and we are now bringing in new sets into the class, or in short making it a larger class. Subject to this restriction that we are bringing in not every subset of X but only those subsets which are subsets of sets of measures. That means we are now enhancing the class of sets which constitute the sigma algebra. So you have a larger collection. Is that larger collection a sigma algebra? This is the question that we are going to ask. We get this property 0. Be a measure space. Let now introduce a new collection of sets. M star is equal to all E subset of X such that there exists measurable sets A and B that is A belonging to such that A is that is E is squeezed between the two sets A and B. With the and for the measure of B minus A equal to 0. Because they are measurable sets, so B minus A is a measurable set. So this is well defined and this is equal to 0. They are working. Okay. So you can consider all sets, subsets of X with the property that such a subset is squeezed between two measurable sets A and B, and the measure of the difference of A and B is equal to 0. Okay. So we essentially enlarge the class of sets. Now you see that you can easily see that M is already contained in it. Okay. Trivially, M is a part of it. Now define mu of define mu E equal to of then the collection M star is a sigma algebra. So this is a step. So we collected all subsets E which is squeezed between two measurable sets A and B with the property that the difference of A and B has its measure equal to 0. Okay. Originally E may not be measurable. Okay. So we have now enlarged a class. I mean, why I say we have enlarged a class? So we make a remark. So you take any, suppose then choose A equal to E. Then what do you have? Now this is E, this is also E. E is squeezed between E and E. And then you have B minus A is empty set. Okay. And therefore measure of equal to 0, which implies E is So that's the first thing that we observe, that this M star is essentially an extension of, okay. So M star now, so the question that you are asking is M star a sigma algebra? If the theorem is true, see, if algebra, then we extend, we measure mu to M star by defining mu of E, mu, this is what we said, okay. Is a, turns out to be but we have to prove all this, okay. So this is the sort of remark that we can, I'll put here remark. Now if all this works, then we say M star is a completion of called a completion of in fact more precisely we say that M star is a mu completion this is what it's called, a mu completion. So we are bringing in more sets into this class and making it, if we can prove that this is a sigma algebra and mu is a measure on M star, then you are done. So that's what we have stated in our theorem. So in our theorem, so what we assert is this. So the theorem that we have is X measures. So let us prove this. the proof. First, you prove that U is well defined okay. So we already have this, and there is no problem about this. We have seen star, and therefore for E belonging to N, measure of now suppose but is an element of then we claim mu of E unambiguously how the ambiguity could come. See, you may have E may be contained in B1. In that case, by our definition, mu of E equal to mu of A1. But it may be defined A may be, so we bring it B. Then this means mu of E equal to mu of A. What we have is mu of B minus A. Okay, here mu of equal to 0. This is the definition. Then mu of but are these equal? If they are not equal, it really depends on what A1 and B1 you choose, what A and B you choose. Okay. So what we claim is this. So first thing that we verify is that our assertion is that mu A equal to mu A1. So we claim this. This is what we want. So that there is no ambiguity about the definition of the measure of E. Okay. So let us prove this. Okay. So you have these two things. A1 mu of E may not be So this is the scenario. Okay. Now let us observe this. So you see that you have A minus A1 is contained in E minus A1 is contained in B1 minus A1. Why? See, this is what you have. E is inside B. This is inside A. Is trapped between. Okay. So A minus. Now you have another. This is B1. See, you have this scenario. This is A. This is B. Now you have another A1 and you have another B1. Okay. Now let us observe this. A minus A1, A minus A1 is contained in E minus A1. Okay. So you have got A A1 here, and this is your A minus A. And you have this scenario. This is C. A is contained in A1 is also contained in. So what does it say? A minus A1 is this portion is contained in B minus A1. Okay. Now B1 is something bigger than all this. So it is contained in B1 minus A1. So we have mu of A1 is contained in is less than or equal to mu of which is equal to 0. Therefore, mu of equal to 0. Therefore, now what more you have? Therefore, mu of A equal to mu of A intersection. This is what you have. You have A here, A1 here. Of course, E is something which contains all these things. This is your okay. Now, what about mu A? Mu A is, see, A minus A1. This is A minus, and you have A intersection A1. This is this part. This part is A intersection. Okay, so mu A is equal to mu of A intersection A1 plus mu of A minus A1. Mu of A minus A1 is 0. Okay, so what we have is this: A is equal to A minus A1. This is disjoint union. A intersection A1, but therefore this is disjoint union. Mu of A equal to mu of A minus A1 plus mu of A1, and this is equal to mu of A1. Therefore, mu A is equal to mu of A intersection A1. Now interchange the role of A and A1. Then we get mu of A equal to mu of A intersection A1 equal to mu of, therefore you see that whatever be the way in which E is squeezed, okay, between A and B or A1 and B1, you always get mu of A equal to. Okay, so that's the first statement. So that part is taken care of. That means mu of E is very different. That is the meaning of that. Now our next claim is that M star is a algebra. This is what we want to prove next. M star is a algebra. So the first thing that you observe is this: X belongs to M star. This is what. Now you see that X belongs to M, and script M is contained in M star, which implies second property. If E belongs to M star, then we want to show that when E belongs to so this is the next one, that is the complement of E. If E belongs to M star, is also in star. I mean, we are basically checking the properties of a sigma algebra. Okay, so for that we make the observation: A complement minus B complement. See, A complement minus B complement is equal to A complement intersection B. This is essentially equal to B minus Okay, that's easy to check on this. So you have got A is contained in E, so you have this solution. Now you take the universal set and then work with this. So A complement, A is contained in B. Okay. So you take B complement. B complement is this one. Okay. Take out B complement. B complement is this one. Take out B complement from A complement. Then what you get? You get B A complement intersection. Now this is very easy to check. Okay. So use that figure. Check. Right. And this is essentially equal to therefore A complement minus implies u of equal to 0. Now you see that E complement is contained in, so you have got A contained in E, B. So you have B complement contained in E complement contained in A complement. Therefore, you see that E complement is squeezed between, so E complement lies between B complement and A complement. And the measure of A complement minus B complement is 0. Therefore, so that's the property. The third property is if AI BI, now define E to be equal to union BI, A to be equal to union BI, so countable units. B equal to now we have to say that E is measurable or E belongs to claim M star. This is what we want to establish. So you easily observe that A is contained in E, E. Now you have B minus A is equal to union 1 to infinity Bi minus A, which is contained in union 1 to infinity Bi minus A. Okay. Now what happens? Mu of equal to 0, which implies mu of union Bi equal to 0. And therefore, union of B minus A. Therefore, mu of and each of this is less than or equal to that, therefore this is equal to 0, which implies mu of, because mu of we are using this. Because countable therefore we have proved that E belongs to M star. Therefore we have proved that Ei star. So that we have. Now what more is to be proved? We have to prove that we are now going to define. So far we have not defined measure on, we have said what the measure of EI should be, but we want to show that it's indeed a measure. So finally we want to verify that if EIs are disjoint, then the same is true for AI. That is clear. And then we have mu of E is equal to mu of A, which is equal to sigma I equal to 1 to infinity mu of AI, because they are disjoint measurable sets, which that means if you have the collection EI M star, then EI Pj is empty for I not equal to j, then mu of I is equal to, this is what we have to do. This is what we have. That means mu is countably added. Hence x mu x m star mu. That completes the proof. It's routine, but to be carefully handled. Okay. So I think that's a place where I would like to stop today and would continue with it later. Maybe in a couple of days' time I'll be back again. Thank you very much.